In this video, we'll use what we've learned about sampling distributions to estimate population proportions. When was the last time you took a survey or filled out a poll? When you did, the person or company that was surveying or polling you was trying to use your responses to make inferences about the population as a whole. The methods that are used to do that come from the stuff we've been talking about in the last couple of lessons on sampling distributions. But now we'll be turning it on its head, because this time we don't know about the population ahead of time. That's why we're taking a sample in the first place. Imagine you work for a polling company, and you want to find out how people feel about a new government program. So you decide to take a sample of people, a simple random sample that is, and ask them, do you support the new government program? Out of the 80 people you surveyed, 56 of them said yes, and the other 24 said no. You divide your number of yeses by the sample size of 80, and you find that comes out to 70% of your respondents supporting the program. That is, your sample proportion, p hat, is 0.7. Based on your results, what can you conclude about the population as a whole? What proportion of the entire population likely supports the program? It may be 70%, just like your sample, but it could easily be just a little bit higher or lower. The amount we think we might be off by in either direction is called the margin of error, which is something you often see if you look at just about any respectable poll or survey. Using our margin of error, we can build what's called a confidence interval, which is a range around our observed value that we think is likely to contain the true population parameter. But how big is our margin of error? 5%? 10%? How can we tell? That depends on the confidence level that we set. Let me explain. The thing we're looking for is our population parameter. In this case, the true proportion of voters who would say they support the program if we were to ask them. We may not know what that proportion is, but it exists. So instead, we take samples and collect statistics. In this case, the proportion of our sample who said they support the program. Sometimes those statistics are above the true parameter, and sometimes they're below. So when we build a confidence interval around those statistics, we're hoping they contain the true parameter. But there's a chance that they don't, depending on how big we make the interval. The percentage of confidence intervals that capture the true parameter is called the confidence level. So for example, if on average 95% of our confidence intervals contain the parameter we're looking for, that's 19 out of 20 for reference, we'd say we have a confidence level of 95%. An important thing to keep in mind here is that confidence intervals are all about trade-offs. Holding our sample size constant, if we try to make our margin of error smaller, we'll get a more precise range that we think contains our parameter. But that would lower our confidence level, which means there's a higher chance that we don't capture that parameter. On the other hand, we could try to increase our confidence level, but that would require that we make our margin of error larger. We're hedging our bets more. So let's see how we can use what we know to figure out a confidence interval for the proportion of people who support the government program. Remember, we surveyed 80 people, and 70% of them said that they supported the new program. Using just this information, we can already make some guesses about our sampling distribution. For example, we know that the mean of all possible sample proportions is just going to be the population proportion. We don't know what that is, but we know that our sample proportion should be pretty close to it. Similarly, while we can't exactly calculate the standard error, we can make a pretty good estimate by replacing p with p hat in our formula. In our case, that comes out to a little over 5%. What's more, notice that if we calculate n times p hat and n times 1 minus p hat, both of them come out to at least 10, which means that the sample proportions are approximately normally distributed. That means we can use all the stuff we know about the normal distribution to come up with a good confidence interval. The relevant thing we can use here is that if we treat our confidence level as an area in the center of a standard normal distribution, then we can come up with what's called a critical z-value, which tells us exactly how many standard deviations away we could be when using that confidence level. The nice thing here is that for a given confidence level, you can always use the same critical z-value. For example, anytime you build a 95% confidence interval, your critical value is always going to be 1.96, every single time. And since 95% is a pretty commonly used confidence level, let's go ahead and use that for our problem. We now have everything we need to calculate our margin of error. All we do is multiply our critical z-value, which remember we got from our confidence level of 95%, by our estimated standard error. In this case, if we work everything out, we get right about 0.1. In other words, that 70% that we got for our sample proportion of how many people support the new government program, we're estimating that the true population proportion might be off by as much as 10% in either direction. That is, we think it could be as low as 60% or as high as 80%. So our confidence interval ranges from 0.6 to 0.8. Great, we found our confidence interval. But before you celebrate, a word of caution on how to interpret it. You might be tempted to say that there's a 95% probability that the true proportion of voters who support the government program is between 60% and 80%. That sounds plausible, but it's actually very wrong. Why? Well, if you think about it, when it comes to the population proportion, either it's between 60% and 80%, or it's not. There's no probability there to speak of. Think of it like rolling a die. Before you roll it, there's a 1 in 6 chance of, say, getting a 5. But after you roll it, there's no probability anymore. The outcome's already been determined. Even if you haven't looked at it yet, either it is a 5 or it isn't a 5. The correct way to phrase things is to say that we're 95% confident that the true proportion of voters who support the government program is between 60% and 80%. This may sound like just semantics, but there's a key difference here. When we say we're 95% confident, what we're saying is that if we were to repeatedly do this kind of poll, asking 80 people each time, then we'd manage to capture the true population proportion 95% of the time. So remember to be careful to talk about not probability, but confidence. So here's an overall summary of everything we've said for confidence intervals for proportions. The conditions under which we can use the normal distribution, the critical z-values for various confidence levels, the margin of error, the confidence interval itself, and the phrase we need to use to correctly interpret it.